So, what about the posters? Is everybody okay with that? Can I erase that? So everybody that needs to print a poster has done that, right? Okay. So my name is Spyros. I have a pretty large or long last name, Chatzivasileiadis. I'm an associate professor here at DTU. I joined about 2 years ago. Before that, I have spent time in Switzerland and the US. And I am actually doing some optimization, but my background is mostly power systems, right? So today we're going to talk about optimal power flow. The first 1.5 hours, we're going to talk about DC and AC-OPF. And then the second part, we're going to talk about convex relaxations for the OPF problem. So before I start, there are some things that we need to discuss. The first is about the poster session that we have tonight, right? So I guess most of you have already hung your posters. And we are going to have a kind of an event during the poster session. So if you have noticed, you have different numbers on your boards, right? And different colors. So we are going to split this 2-hour slot into 4 parts. And every half an hour, we're going to focus on a different color. So we're going to say, for example, that for the first half an hour, we have to take a look at the poster with the blue color, right? The blue dot. The idea is that by the end of that poster session, you are going to vote who is your favorite poster, okay? And you must not vote for yourselves. So what we're going to do is we're going to award like the best poster session, like the poster session award, right? So the most popular poster, this could be we don't define any criteria, but what we would like you to vote for is actually what you think is the most interesting work, right? What is the most interesting for you? So this means that we are going to have 4 slots. We're going to focus on a different set of posters in order to give you more room, let's say, to go and visit as many posters as possible over these 2 hours. And during dinner, actually, we're going to have this award. Along with that award, we will also have the awards for the Mosaic scholarships and the DTU scholarships. So Erling Andersen, the CEO of Mosaic, will be with us during dinner and will present the awards. Yeah, and about the poster session, you are going to get some more information when we start. So Thanasis, who is actually the moderator for the poster session, is going to give you more information. Any questions? Anything I'm forgetting? Okay. Are you ready to start? So I hope you had some good lunch and some strong coffee, because we are going to go a bit hardcore. But not from the beginning, okay? So the first thing I want to ask is, first of all, how many of you have been introduced to power flows, have done power flows in the past? Okay. So how many of you know about phasors? Okay. What about optimization? How many have heard about Karuskun-Tucker conditions? Okay. And have you solved a linear program? What about a nonlinear program? SDP? Semi-definite programming? Second order cone? Okay. This is just for us to get an idea of your background and see how we can actually adjust the talk. So what is an optimal power flow? So as you understand, I have to give you like a common base, right? So some of you haven't heard of optimal power flow before. We're going to start gradually. So the ones that have actually computed or implemented an optimal power flow, what is an optimal power flow? You have to raise your hand and actually speak up. Yeah, great. Yeah?
Do I need the cube or?
Actually, you do.
Became a habit. So the optimal power flow, from my understanding, is the optimally distributed power in the transmission network, by considering the network constraints, technical and non-technical, I can say.
Very nice. Anybody else would like to add something? Okay, let me formalize that a bit more. Right? Optimal power flow is an optimization problem. Optimization, we can optimize many different things. With optimal power flow, what we're doing is we have an objective. We try to achieve that objective, for example, minimize costs or minimize losses, subject to the network constraints that you said, right? So in the general case, the optimal power flow is a non-linear and non-convex problem with thousands of variables, right? And I think this is also what Miguel mentioned in his talk before. What we're going to do here is we're going to provide the fundamentals. So we're going to provide the fundamental formulation for both DC-OPF and AC-OPF, where you can build on it. Real optimal power flow problems have so many constraints that none of us actually can think of if we don't really have the problem in front of us. Okay? But having this fundamental, you can build on it and extend in the way that you want. So what we do here is we have different objectives. We can minimize costs, we can minimize transmission losses, right? And we have different constraints. The most important of them is that the supply must always meet the demand, right? And then we might have different limits, operational limits in terms of generation or voltage limits and things like that. So this is what the disclaimer is about. I mean, you can also find the slides online. And I have tried to be more complete in the slides so that when you read back, you, let's say, to be more correct in what we say here. So for this 1.5 hours, we're going to have also a break, so we should not worry about that. But we're going to talk about economic dispatch, DC-OPF, and AC-OPF. Okay. So what is economic dispatch? Yeah, one.
I would say the simplest approach of optimal power flow because you neglect the constraints of the power system. You assume a copper plate model where you just care to dispatch a generator to satisfy the demand.
Right, right. What about DC-OPF? Based on your, yeah, please go ahead. This is going to actually take too long if we do that every time.
It's what we just saw in the previous lecture.
Right.
No? So you approximate the network by the DC relaxations where you basically only consider the voltage angles as the driving force.
It's I won't call it DC relaxation. It's linear approximation.
Yeah,
okay.
sorry, did I?
Yeah.
I mean.
Yeah, yeah. Just to be correct. What about AC-OPF? Yeah, yeah.
AC-OPF stands for alternative circuit optimal power flow. So instead of a linear approach in DC, we have non-linear case here. So it's harder to solve in some senses.
It is. Thank you. Okay. So what I really want to make very clear here is we talk about DC-OPF and AC-OPF. This has nothing to do with AC and DC current. Okay. In the past, we had no HVDC lines, no direct current flows. So people thought, okay, let me approximate the nonlinear functions or the nonlinear equations of the alternating current with a linearized form. And I call that DC. Okay. But DC and AC-OPF is just, let's say, relics of a previous time, and we still use it. They are still valid, but they have nothing to do with AC, with alternating current and direct current. Okay. When we talk about DC-OPF, we mean the linearized version of the optimal power flow. When we talk about AC-OPF, we mean the nonlinear version, which is actually the exact power flow equations. And that must be clear. Okay. I can have an AC-OPF with HVDC lines. And I have the DC-OPF is primarily for AC networks with DC as well. Okay, please, Han.
Yeah, I have a question. In terms of the time frame, the transmission system operator, they solve as economic dispatch. in the day ahead market and an AC-OPF every hour ahead, or how does it work?
You can solve an economic dispatch every 5 minutes if you want, right? The thing is that the AC-OPF, so the operator does not really solve an AC-OPF. So if we really want to go into the real world, economic dispatch is something that has been applied for several years. DC-OPF is something that is actually very well used in the markets, both in the US and in Europe. AC-OPF, there are very, very few operators that do something with OPF. Okay. I know from RT in France, they have developed an OPF in their research department. They are actually pushing as much as they can so that the operation department can actually adopt it. And they still have problems there. In ISO New England, they are now trying to solve an AC optimal power flow for their market. Okay. Denmark, they don't do that. Right now, they actually have a task force. They are going to build their own optimizer. Okay, their own solver to solve their AC optimal power flow. So this is, you can see that as a barrier, but you can also see that as an opportunity. I mean, our job here is actually to get educated in these concepts and then move to the utilities and convince them that this is the way that should be done. Okay. And it's our job to build robust solvers and robust solutions that can actually be used in real life. Okay. Okay. Some more things about the, I hope this works. Yeah, about what economic dispatch is. So this is usually used in power exchanges. You might have heard of that, or power pools. As Juan said, the only constraint is that supply must meet demand and the generation limits. Okay. Then we have the DC-OPF, which is used in nodal and zonal markets. Nodal, most of it is in the US. Zonal is what we have in Europe. It considers the power flows, okay, and the line limits. However, we have only the active power. We don't take into account losses or reactive power, okay. And the AC-OPF is, let's say, the full-blown problem. We have the exact equations there. There is a report from FERC, is the Federal Energy Regulatory Commission in the US. They said that the security constraint AC-OPF is the ultimate goal for market software. We are not there yet. Solving a problem with thousands of variables or tens of thousands of variables is actually a very demanding task. Okay. It's our job actually to make that better. So with an AC-OPF, you don't only do it for yeah, please.
Because also, like in some markets, like day-ahead markets, I think it's possible to submit block bids, which are like, if they are accepted, they are for several periods.
Yeah.
And when this is done by the market operator, is this like, this is an economic dispatch, right? Or
if they don't take the market, the network into account, it's economic dispatch.
Yeah.
Depends where you bid that.
Yeah, but then this is like, I mean, there is coupling between several periods in an economic dispatch, but in DC or AC-OPF, usually you don't have coupling between several periods, or
you could.
You could, okay.
Yeah.
Yeah.
It's just, I mean, you enlarge the problem, but you could have coupling as well.
Yeah. Okay.
Right? So you can, maybe you can keep it there. You can just turn it, flip it, so that. Yeah, so, and then with the AC-OPF, we don't only optimize over active power, we can have minimization of losses, we can, let's say, optimize the voltage profile. What's also important is that the linearized version, the DC-OPF, is good for transmission networks, but the approximations that we make, they are not as good for the distribution, okay? So if you really want to do an optimization in distribution networks, you better use AC-OPF, okay? And if you were submitting a paper with DC-OPF on distribution, it's not going to be as well received as if it was with the AC equations, okay? Okay, so let's discuss a bit about the economic dispatch. So the goal there is to find the cheapest generators that can cover my demand. And I need to formulate that as an optimization problem. So we said that the optimization has an objective function. We want to minimize something, and we have some constraints. So how do I formulate that? You have this ball over there. Please pass it along to somebody that can. Wait. Who is going to? Guys, there are 3 people that are participating, 4. I understand it's after lunch, but let's get a bit more active. Eh?
Well, our objective is to minimize the cost of the generating cost, and then we can first see what the components of this costs are. There may be an operating cost and a cost for starting up or shutting down.
So minimize generation costs?
Yeah, and so it would be the sum of the generation costs during the individual periods over our planning horizon.
Okay, let's suppose that we have one time period, right?
Okay, yeah, so it's the generation cost, then plus possibly the the starting cost.
Okay,
Yeah.
but this is more for the unit commitment. I'm just talking economic dispatch.
Okay, so then subject to
Yeah.
meeting demand totally. So what meeting demand means is that the sum of the output of all of our generators.
So I will call that sigma PG, right? All of the generators, right?
Yeah, should equal
Yeah.
the demand.
Yeah. So the sum of all my loads, right?
Yeah, so this is now, of course, assuming a deterministic problem.
Yes, we're talking only deterministic here.
Okay.
Is that all?
No, because the load would be a parameter, but the decision variables is our production.
Right.
And that means we should introduce some bounds on this production.
Indeed.
And these bounds would be that the production should be non-negative, and it should be bounded above by the maximum, the nominal capacity of our generators. And it may also be bounded by some influence of our previous
We're good. That's all.
production.
Okay. So I'm going now to change the generation cost. I'm going to assume linear costs here, so I just have one factor CI times PGI. Okay. So for every generator, I have a cost. This is, if you want, dollars per megawatt hour. Okay. That's my CI. So this is what, for example, different generators bid in a power exchange. This is my cost. Then what the market operator does, takes these costs, takes also the limits of the generators that they have all submitted, has an estimate for the demand, and clears the market based on that. So I have to find the cheapest set of generation that's going to cover my demand, okay? Can I solve that? Is this clear? Any questions? Can I solve that without actually optimizing? So without using a solver? How?
Complementary modeling.
That's too advanced. No. What's the bit?
You take the cheapest generating block, you fill part of the load, then you take the second one, you fill part of it, and the remainder.
Great.
It's separation.
Everybody agrees? Yes, with in a more general case, that's true.
Yeah, because it will try to do problem, and that's the solution.
Yeah, so the simplex actually is going to solve it like that. Yeah, the simplex solver. But let's try first to do that without any. So this is, let me first say that as well, before I'm going. So what David actually said, and we're going to see in the next slide, is a merit order curve, okay? Before going there, just give me 1 second to talk a bit about that. That here, we haven't considered any network constraints. Okay, here we just have the generators and that they must cover the demand, right? So how the power flows over the lines, we haven't considered that. if the flow is actually exceeding the line limit, we don't really know. And the economic dispatch does not care. Okay. So what we say here is that we assume a copper plate network, and maybe you have heard about that several times. I have heard that a lot during my PhD. I didn't understand what a copper plate is. Okay. Until actually I realized that they really mean a copper plate. So what this means is actually is that you can assume that everything is so well connected with each other that there are no constraints that have to do with the network. Okay. So the power can flow from any point to any other point without any constraints. And that's what a copper plate is. Good. So, and now that's what we'll go with David said with the merit order curve. So what we do here is we rank each generator from the cheapest to the most expensive one. Okay. And this A, B, C, and D is actually the maximum limits of this generation. So we add this up and we try to find where is our demand, right? So, and let's say that our demand is so much for the next hour. So if it is so much, then what we're going to do is we're going to dispatch this generator, and this one, okay? And then the price that we call the system marginal price is going to be the price of the last generator that got dispatched. Okay, that's the price in a power exchange setting. That's the price that all generators are going to get. It's a uniform price for all generators that have been dispatched. Okay, good. Questions? This is an example of a merit order curve. Okay, this is from Germany about 10 years ago, but you can still I mean, this is how operators used to do that, especially also before the unbundling, how they would dispatch their generation. You can see that the cheapest one is actually nuclear energy. Then we go into coal, different kinds of coal, and then gas and heat, and then only gas turbines, and at the end, the most expensive ones are the diesel generators. Okay. Okay, so I'm moving to the DC-OPF formulation. And the problem is that as soon as we get the line constraints in, we might have congestions. Okay. So you can think of that in the most simple power system, which is a two-bus model. Okay. And let's suppose that this has $60 per megawatt hour, and this 120. And I have here a load of 150 megawatts. And this is 200 megawatts and 100 here. Okay. If we don't take the line constraints here, so I don't care what this is, what's going to happen? Right. The left generator is going to supply all the demand, right? If I assume here that I have 100 megawatt limit, the left generator can no longer provide all my load, okay, the power for all the power for my load. So I have to dispatch this 100, which is actually can provide much more, right? But I have to go to 100, and then the 50 must come from here. And that's what happens here. And actually, you can prove that if you want. If you take the DC-OPF with linear costs, you can prove that if there is a congestion, I'm going to have two marginal generators. This means that there are two generators that are not dispatched to their minimum or maximum capacity. Okay. So as soon as I have a congestion, I'm going to have to dispatch another generator, which is going to be more expensive, and in order to cover my demand. Now, by doing that, you are going to see in the DC-OPF that you are going to get different prices. So we no longer have a uniform price for all of my area. but I'm going to have different prices on different nodes. Okay. So we talked a bit about that. The question is now, since we want to include the line flow constraints, how do we do that? And this question is actually addressed to you. That's my economic dispatch, right? But this is not enough. Yeah, David.
I just have a question before we
Yeah, please.
DC-OPF. Okay, so before we move to DC-OPF, you said that the economic dispatch is basically used to clear markets, right?
It's used to clear power exchanges. Yeah.
Clear power
So
exchanges.
parts of, yeah, types of markets. Yeah.
But since it doesn't represent reality, so you have like no congestion possibilities. If you add those line constraints, then you will have different prices. So basically the marginal system cost as provided by the economic dispatch is not the actual cost of the system. So what's the rationale behind still using economic dispatch?
Okay. So the price is going to be set from the market. And if you have a power exchange, the price is going to be the same all over your market area. Now, these decisions are actually transferred to the operator, okay? And then the operator is going to see that there are line constraints. I'm sorry, I cannot actually dispatch this generator as much as you thought you can, okay? But this generator is going to get paid and reimbursed for the power that it cannot produce. The operator must pay extra costs for this kind of redispatching. So the operator takes the decision from the market, and this is not only for a power exchange with economic dispatch, also for the DC-OPF, because the DC-OPF is also an approximation, okay? So the operator takes the decisions from the market and runs power flows and tries to see, is my system secure with his decisions? If my system is not secure, I have to do redispatching, and I have to pay for that. And I have to compensate the generators that were actually dispatched, but they cannot because it's unsecure. And I have also to pay the generators that have to operate because to cover my demand. Okay? And this is how it happens. So there are two different processes. Any other questions? Yeah?
Suppose that you also have a price on your line.
A price?
Yes.
For what?
For transmitting. Who is going to pay the transmission?
So it depends on the kind of market you have. You used to have this kind of what we call explicit capacity allocation. And in that sense, this was especially, at least in Europe, you had to pay for the capacity that you were going to need to transfer the power. And then there was a different trade for how much power you want to sell. What happens right now in Europe is that you have this kind of implicit capacity allocation. What this means is you run an OPF, and implicitly the capacity of every, you reserve capacity on every line that you need, right? So you no longer need to pay extra or on top of that. And in the nodal pricing scheme, this is also the same.
And in your case?
In which case?
The figure you have down there. Actually, just on the blackboard.
Ah, here, yeah.
Yes.
So it depends what kind of market you want to. If you want to go about economic dispatch, then yes, you have to reserve capacity, right? If you go with DC-OPF, then automatically this is calculated during DC-OPF. Okay. Other questions? Yeah.
Who pays for the losses?
The operator. And actually, to be honest, the consumers. Because everything is going down there, right? Yeah. So what happens, for example, in Denmark, right? We have the market dispatch, and then the operator takes these values and puts it in the system, and they have an estimate about the load, so they have an estimate about the losses, right? And I'm going to that market, and I am buying for the next day. I have this estimate. So actually, I don't know the dispatch yet, but I have an estimate based on historical results, what the losses are going to be for the next day. So I'm going and buying from the market this generation to cover my losses, okay? And the way I do it is I bid with the highest possible price So in Denmark, they bid, for example, with 3,000 euros per megawatt hour. This is like the top they can bid because they don't want to distort the market, right? And at the end, they pay what is the most expensive price in Denmark for a generator, which might be 60 or 120 or whatever. But they don't want to distort the market. So I have now secured some power to cover my losses. But of course, the next day, we don't exactly know how many the losses are, right? And then I go to the balancing market, and I buy the rest, either plus or minus. Clear? OK. Yeah. Where is the, yeah?
I had a question about the prices which you pay in relation to the LMP, and what you mentioned is that if there is any congestion or any network violation, it will be the consumer who pays, but or it will be the system operator. So just to get a clearer understanding, if, for example, there is a like the LMP is comprised of the marginal cost of generation with the network operation cost, the system congestion cost, plus the network losses, right?
The operator has to pay for the congestion cost and the losses?
Yes, because that's how LMP is formed.
The redispatching, yeah,
Yes.
yeah, but so the operator has to pay for the redispatching costs and the losses.
Okay.
The congestion cost is just part of the economic theory, and it's actually a revenue for the operator.
Okay. So in that line, the consumer would, like, the congestion surplus is still collected. How is it set up in Denmark or over here? Like, is it the congestion surplus is collected by the system operator, or how does that work?
If the consumer surplus is connected by the system operator.
The congestion surplus, which is caused. So if you have a congestion in the network, so.
The thing is that Denmark is considered a zone.
Okay.
And there's no congestion inside the zone. The congestion is between countries, right? So then, if there is a congestion between Germany and Denmark, then yes, one of them is going to make profit. If we are exporting to Germany, then Germany is going to have a more expensive price, and we are going to get this kind of surplus.
Thank you.
What are the normal rights, for instance, for allocating this capacity? If I'm a generator and the load center is London, the system operator would like me to place my new generation plant next to London, but I may want to install it in Scotland. So is there a thing that the system operator can do to force me to be clear to the
I'm not an expert in, this is a regulatory issue, to be honest, okay? And I'm not an expert in that. Maybe Jalal can also. But the thing is that you cannot, as an operator, you cannot tell them you have to install it there, except if it's a matter of security of the system, right? They can deny the installation maybe of a generator if it's a very important matter for like if there's a blackout. But what they can do is they can give incentives. And this is not the operator, but the regulator must give incentives because it's better for the social welfare.
Okay.
So it's better for the society. But that's how they can deal with it.
Thank you.
Other questions? Okay. So, formulation of the DC-OPF. How do we include the line flow constraint? Yeah.
Yeah, now instead of having one overall balance equation, we need to write one balance equation for each node. And then we need to say that the flows that we have between the nodes need to respect the capacities of these arcs.
So let me, yeah, it's correct. So what I really want as a constraint, right, is to limit the line flows. And as Miguel presented in the morning, my line flow is going to be, in the DC-OPF context, the difference of my voltage angles times the reactance, the inverse of the reactance, must be less than that. Okay. So what happens here is I model my line with reactance Xij, and we're going to discuss about it shortly, but I'm taking the voltage angles, the reactance, I formulate this equation, and this must be below the limit. What's the problem here now? If you think of it as a system of equations, right? I have an optimization. I'm trying to minimize PG. That's my only free variable, right? And because it's in the objective function, it's going to find something that's actually going to minimize that. And this free variable must be equal to some constant and must be between these limits, right? But now I have the thetas. And if these thetas are constant, then I cannot move anymore with my PG, right? If these thetas are free, they are too free. I have somehow to connect thetas with my PG. So because I need thetas in order to define the power flow or the line flow, now I need an extra set of equations to connect my thetas with my optimization variable, or my real, so what I really want to optimize here in this PG. Is that clear? And that's how we go to the node balance equations that you talked about. Yeah, so let me go first here, and that's what I talked about. And these are the node balance equations. Now I'm going to take a step back, though. And we're going to see how we actually get the line flow constraints. So what you see on the left over there, this comes from the AC power flow if I assume that here my line is modeled as a series reactance, right? So no ohmic resistance, no other shunt capacitors, just a series reactance. That's what I get. And this is the active power flow. And what I do now here is I actually linearize that, because you see here we have VI, Vj, this is a quadratic term, and I have the sinus. So the question is, first of all, what are my assumptions for linearizing? Can put over there.
That they're both very
over there.
We assume that our voltages are close to 1 per unit, for example, to get the 1 above this division. And then you also assume that sine theta is approximately theta, if the angle is in radians.
That's great. Very nice. That's very important as well. I have it also later in my slides. The angle must be in radians. And if the angle is in radians, sine theta equals theta if theta is relatively small. And the rule of thumb that I have seen, let's say, around is about 30 degrees. That's small. OK. So if you go up to 30 degrees, usually sine of theta is equal to theta in radians. And voltage is equal to ampere unit. So having now this approximation, we go and put it in the optimization problem. What's important here is that this is the absolute value. Of course, this is not linear, but it can easily be split into two linear constraints, right? Minus and plus. I guess that's straightforward for most of you. It is in absolute value because we must take into account both directions, from I to j and j to I. Okay. And I have seen people forgetting that. Good. And then we have to include the nodal balance equations. Now, for the node balance equations, okay. The matrix B, does anybody know how we call that? Right. It's the bus admittance matrix. Very nice. The bus admittance matrix. B. That's matrix B. And we're going to see how we actually build that matrix. Theta is a vector, and it's actually a vector of all my angles that are, so you have one angle for every node, right? PG is a vector, and it's again the generation on every node. If I have no generation on a node, it's going to be 0. and load the same. If I have no load on the node, it's going to be 0, that element there. If there is load, then I'm going to put the value. Let's assume a 3-bus system. I'm having 2 generators and a load. So PG1, PG2, PL, okay. And this is X12, my reactance, X13, and X23, okay. The bus admittance matrix is nothing else than the sum of the power that flows. So the power that flows from PG1, right, where does it flow on? It's on 2 lines, the 1, 2, and 1, 3, right? So I can write here that my PG1 is equal to P12 plus P13. Okay. But now I have an equation for how much P12 is, right? Because P12 is 1 over X12, theta 1 minus theta 2. That's my line flow. So 1 over X2, theta 1 minus theta 2, plus 1 over X13, theta 1 minus theta 3. Now what I want to do is I want to group common variables. So I mean theta 1 times 1 over X12 plus 1 over X13 plus theta 2, 1 over X12 plus theta 3, 1 over X13. Questions? That must be clear, right? But my question is now, how do I put that in a matrix form? Because what I have over there are matrices. So what I want to have here is actually, I will start with PG1, right? Equals to something. Let me, PG1 minus PL1. Theta 1, theta 2, theta 3. B times theta, theta 1, theta 2, theta 3. Please. Yes, you're absolutely right. Thanks. Thanks for that. How do I build this matrix? No. I decide. No, thank you. But I need a new one. No. I need somebody that hasn't spoken yet to join and actually let us know how we're going to build that matrix. Yeah, over there, please.
So you just add ones and zeros. So the first line would be, if you want to do theta 1 minus theta 2, so the first line will be 1 minus 1, 0.
I want to express that, right?
Yeah.
Okay. So where is that theta 1 minus theta 2?
I mean, do you want to build a matrix, if I understood
Yes,
correctly,
yes.
that needs to be multiplied by the vector thetas?
Right.
So that you get to...
Exactly, yeah. So what I'm going to put, so...
all right, so you just put the 1 divided by x12, 1 divided by x13, no?
Yes. So the first element is going to be 1 over x12 plus 1 over x13, right?
Yeah.
Yeah, then?
And then you need to multiply by minus, you need to get the minus theta 2, so that will be minus 1 divided by x12.
Yeah.
And then you need a minus 1 divided by x13.
Right. Right, great. Yeah. This line times this column is going to give me that expression. And this is equal to PG1 minus PL1, that is 0. So we could actually go all the way and actually build that matrix, but there is a simple rule that you can always follow. And the rule is as follows. On the diagonals, I have all the susceptances. So 1 over x12 is the susceptance, is the inverse of my reactance. I have the sum of all susceptances. So if I go now to, let's say, 2, 2, this is node 2. Node 2 is here. What's going to be on the diagonal on the second row? Here? Right. The sum of the susceptances. Yes. OK. So on the diagonal, it's always positive and the sum of the line susceptances that are connected to that node. On the off diagonal is the minus of the susceptance that connects these two nodes. So here's, for example, element 2, 1 is going to be the line connecting nodes 2 and 1, the minus of the susceptance. Okay. If there's no line connecting those nodes, 0. Good. Questions? If there are no questions, then there's an exercise. Yeah.
So in your expression, the power are expressed in per unit?
Yes.
So also the reactance?
The reactance is also in per unit, yeah, and that's also very important. Because we're also, yeah. Since the reactance is in per unit, radians are dimensionless, we need to have power in per unit.
So, and what about the cost? They are also in dollars per megawatt hour? Or?
Yes, but you can actually either have a factor in your objective function to express that so you can have your base MVA, let's say, in your objective function. But it's not going to make a difference for your optimization. It's just a constant. So it's a constant factor that is going to be multiplied. You can either have it in the objective function, or you can leave it as it is. But at the end, you're going to know that it's not 1.2 per unit. It's actually 120 megawatts, right? OK, let me say that again. Let's go here. So let's suppose that I have a base power of 100 MVA, right? So this is in per unit. Here I can have, let's say, an x12 equal to 0.1 per unit, right? And I have a base power of 100 MVA. So this one here is going to have a limit between 0, PG, 1 per unit, right? This one here is going to have a limit of 0, PG 1, 2 per unit. My optimization is going to figure out that somewhere, so this is going to be like 1 per unit, and this is going to be 0.5. If I have the factor in there or not, it doesn't really matter, as long as I know that at the end, I must transform the cost to the real cost, right? So if this is $100 per megawatt hour, or if it's $120 per megawatt hour over 100, it doesn't make any difference for my optimization. Shall I say that again? OK.
So there will not be difference for the dispatch?
No, because so what's going to happen here is going to be 120. OK, I have to actually somewhere write the objective function. I'm going to erase that. That's my objective function, right? My objective function is going to be minimize 60 times PG1, right? Plus 120 PG2. Is that correct? 60 times PG1, 120 times PG2.
In megawatt.
Indeed. So if I want to get dollars per hour, this must be in megawatt, right? But I can also have 60 times PG1 over 100 plus 120 PG2 over 100, right? Now this is my per unit. I can have 1 over 100 60 PG1 plus 120 PG2. It's the same thing, right? So if you want to have that in your optimization, you can have it in your program. It's not going to have an impact on your solution, except for the numerics. So sometimes, because of numerical stabilities, we want to have objective function values that are close to 1. It's a little bit more complicated. Let's forget that for a moment, but I'm going to get back to it, okay? In terms of mathematics, either if you have this constant factor in there or not, your optimization is going to converge to the same exact result. You just have to remember, if you don't put the factor here, so like, because this must be now 100 times, right? You must add it later in your total costs. When you try to interpret your results, you must have the 100 somewhere, right? But the solver will not care. Is that clear? Okay. Now, I'm going back a little bit to the optimization solver before we get the break. If you go into the parameters of your optimization solvers, you're going to see that there are tolerances, okay? Because after all, these solvers work numerically, and they try to converge the solution. And if the tolerance is below a certain value, for example, for the objective function, then they say I have found the optimal solution, okay? If I'm working with millions in my objective function, the tolerance value that's going to be 10 to the minus 8 is going to try to converge to something that's like 100 millions, comma, and 8 zeros. But to be honest, for our problem, we don't really care for the 8 zeros. We are talking about millions. If it's like 100 million 1 or 100 million 2, it's going to be more or less okay. So just again, in order to save a number of iterations, and if you have very complex problems, in order to arrive to a solution faster, and in any case, it's not a big difference for you, you actually add these constant factors to move to something that's around 1 or maybe 10, I don't know, depending on how exact you want to be. So if you add a constant factor here, and you go for 100 million to 1 point something, then this means that you have actually divided by 100 millions, right? And then you have to multiply that back. Your tolerance then is going to be about 1. So 100 million 1 or 2. Is that clear, or shall I say that again? Is that clear? Okay, let's have a 15-minute break and we continue.